All right, maybe we can get started. We're really delighted to have Erez Urbach here today, telling us about the black hole string transition in AdS space. You're going to be here until the middle of next week, right? So we'll have a lot of fun talking to him. We'll also be going to dinner tonight. Anyone interested in joining, just get in touch with me. We'll gather in the lobby at around 6 o'clock. Take it away.
Thanks, Nima. Thanks for the invitation. So I'll start by reminding you what's the black hole string transitions. And then I'm going to talk about my work. That's going to work. Yeah. Okay, so consider we can couple the string theory first in flat space in RD+1, where D is the number of spatial directions, and consider having it roll over a black hole microstate state labeled by the Weizmann radius RH. The micromechanical version of the black hole string transition asks the question of what happened to these states as you adiabatically shrink the black hole size RH down to the string scale LS. And the conjecture is that as you tune the horizon radius to the string scale, the correct description of those states are nothing but high energy string theory excitations. So we have one phase, which is the thermodynamic phase of black holes. We have another one, which is the thermodynamic phase of the string excitation. And the conjecture, the question is, the belief is that these two phases may be smoothly enough related to each other, at least high enough. So this idea is very old. This was first studied in the 80s, then later by Susskind, and in the formalism we're going to use by Horowitz-Polchinski. And specifically, we're going to consider a canonical ensemble version of the transition, where instead of the Lorentzian Schwarzschild solution, we consider the Euclidean Schwarzschild solution, labeled by the asymptotic size of the thermal direction beta. The Euclidean Schwarzschild is the solution in which the thermal direction closes at the point, which used to be the horizon. And again, we're asking the question of what happened when we, instead of turning the horizon radius to the string scale, we turn the temperature, the inverse temperature beta of that solution to the Hagedorn temperature of the corresponding string theory. But this is what I'm calling beta H. And the claim will be that the correct description of this thermodynamic phase is just the thermal solution, RD times S1 beta, just deformed by a winding string condensate, strings winding around the thermal direction. This is what I'm calling a string star. Okay, so the conjecture is, the question whether an Euclidean Schwarzschild saddle is continuously connected to the thermal saddle RD times S1 at the Hagedorn temperature, we're slightly away from the Hagedorn temperature. It is the formation of that solution by a normalizable condensate of strings winding around S1. This is the description suggested by Horowitz-Polchinski and later by Sen and Witten, where they also argued why, at least for type 2 theory, there is at least some sort of phase transition between these two ones. By a Schwarzschild description of these solids. So today I'm going to discuss what happened in anti-de Sitter space to that transition. Now, instead of the Euclidean Schwarzschild solution, we will consider the AdS black hole solution, again labeled by beta. Beta is now going to be the CFT dual temperature, and it's going to describe the asymptotic growth of the thermal direction close to the boundary. But again, we're going to tune beta to be close to the Hagedorn temperature now in anti-de Sitter space. This is what I'm calling beta C. And similarly, the claim would be that this phase is now described by what I'm calling an AdS string star, which is just the thermal anti-de Sitter space saddle deformed by a normalizable condensate of strings winding around the thermal direction close to the origin of thermal anti-de Sitter space. So that would be a similar conjecture now in anti-de Sitter space. It's the small AdS black hole is continuously related to the thermal AdS solution by a normalizable winding string condensate. So why should we study this in AdS as opposed to flat space? So quantum gravity in anti-de Sitter space is much better understood compared to flat space. It is natural to check how the black hole string transition appears, how it carries also to anti-de Sitter space. And second, in anti-de Sitter space as opposed to flat space, we have a holographic duality, and we can use it as usual in two different directions. First, any prediction we will have on these AdS string stars will carry to the holographic CFT dual, and specifically we're going to match results with theories like N=4. And second, it is possible to draw speculations about this transition using the weakly coupled CFT description. Okay, so this is the structure of the talk. First, I'm going to describe the behavior of AdS string star with spatial dimension bigger than 2. Second, I'm going to separately discuss AdS3 string stuff, where they have their own physics. And I'm going to discuss them with backgrounds with both mixed and pure mixed R and NSNS and pure NSNS backgrounds. And thirdly, I'm going to discuss, if I have the time, a similar situation that happened for confining theories. We have what we call winding string gas saddles, also correspond to normalizable winding string saddle. Okay, so first, special direction bigger than 2. So consider the string theory partition function on asymptotically thermal AdS d plus 1. This can be written is what we call Z AdS beta. It can be written in some of the semi-classical saddles. And this, of course, holographically dual to the CFT partition function on SD-1 times S1 beta. The beta is again the CFT temperature. As we know from Hawking page, there are 2 important saddles. One is thermal AdS, that I'm writing in this way, where T is compactified with T plus beta. And in my convention, it has a Euclidean action I of beta equals 0. And has the following metric. And the important figure to remember is first that rho is the radial coordinate, rho equal to 0 is the region, and rho goes to infinity is the boundary. And the time direction grow exponentially with rho. And at rho equal to 0, the size of the thermal direction is beta itself. So beta also serves as the temperature at the origin. And second is that the one loop diverges at the AdS Hagedorn temperature, just like in flat space, just with slightly different temperature, at the temperature that we call beta C. It is also of order LS, just like in flat space, to the order. And the second solution is the Euclidean AdS black hole, which I'm not going to write, and it's reliable whenever the curvature is small, which for the small AdS black hole is for temperature low enough compared to the Hagedorn temperature. Otherwise, we need higher derivative corrections. And phase map of the system looks something like that. So here we have on the y-axis the Euclidean action of each of the saddles, and at the x-axis the inverse temperature. The gray, the horizontal gray line corresponds to thermal AdS. In my convention, it has Euclidean action 0, and the black line corresponds to the thermodynamics of AdS black holes. This line over here goes all the way to the bottom and all the way to the left, such that for high enough temperatures, the dominant solution, the one with the lowest Euclidean action, is the AdS black hole. But for every such temperature, there is also another bunch of solutions, these solutions, that correspond to what we call small AdS black holes, and they have Weizmann radius and smaller, arbitrarily smaller compared to the AdS scale. So closer and closer to high temperature, they can be approximated just by the flat space solution because they're small enough compared to the AdS scale. And the question we would like to ask is what happened to the small AdS black hole when we go to temperatures where we need to consider higher derivative corrections. So for temperatures close to the string scale over here. And the answer that we would like to suggest from flat space is that there exists another solution, another saddle that we call AdS string star, that starts its life at the AdS Hagedorn temperature over here, then goes to lower temperatures, and that's the characteristic picture that you should have, that the two solutions extrapolate to the same location in terms of the thermodynamic properties. AdS string star and the AdS black hole, small AdS black hole. So that's the same conjecture I said. And of course, because we are in AdS, you can also try to interpret this conjecture also in terms of the CFT side, that on SD-1 times S1, to the degree that you have a large N effective action, in recoupling it has a complete meaning, then the claim is that the deconfined phase that corresponds to this black line is continuously related to the, or continuously enough, related to the confined phase at the Hagedorn temperature over here, because you can follow that trajectory. And from recoupling, we did see that that's what happened. Okay, so how do we find these solutions explicitly? So let me remind you the effective action written by Appik and Witten. So for flat space, from thermal string theory on flat space, RD times S1 beta, close enough to the Hagedorn temperature, we have the following effective action. So by near Hagedorn, I mean that beta minus beta H is small compared to the string scale. And the effective action is not just the supergravity action, as you might expect, but also include this new field chi. So what is chi? Chi is the field. I forgot to say that we reduce on the thermal direction S1, and you have an effective d-dimensional theory. And in that theory, you have a field, complex scalar chi of x that is associated with the first winding mode of string theory around S1 beta, and has mass in string units proportional to beta minus beta h. Hence, it becomes massless at the Hagedorn temperature and causes the one loop instability that I was describing earlier. And the other field that we see here is phi, which is just the metric back reaction. GTT is exponent of 2 phi. So altogether, you have this complex scalar here that has its own mass that I wrote over there, plus a kinetic term for phi, plus a leading cubic interaction, phi chi squared. To get only this effective action, you need to have the following assumptions. First, you need to tune the mass to be light enough for you to ignore the rest of the string spectrum. That amounts to tuning the temperature to be close enough to Hagedorn, and as I was describing. Similarly, you need to assume that the profiles of phi and chi have characteristic size L, which is much bigger than the string scale in order to have alpha prime expansion. And finally, you need to assume that the amplitudes of chi and phi are small enough so you can ignore higher terms like chi to the power 4, etc. Under this assumption, you can use this effective action. And you can also copy that discussion to anti-de Sitter space, where instead of the flat space metric, you have the AdS metric, but otherwise, you have very similar looking effective action with the following differences. First, the time direct, TT metric is related to phi now with this cos square term over here. So phi corresponds to the deformation from the thermal AdS coordinate. And secondly, the mass of the particle now has, instead of beta, it has beta cos rho, because the size of the winding string is proportional to GTT, to the square root of GTT itself. If you expand that to leading order in rho, you get to leading order at rho equal to 0, the flat space answer plus a leading correction that's proportional to rho squared over LADS squared. At the end of the day, that would be the leading order difference between the flat space effective action and the AdS effective action. That leading correction to the mass. So that is the important term when you study the effective action at thermal anti-de Sitter space. And we have the same sets of assumptions. The only difference is that to make this effective action looks like that, you also need to assume that the size, the profile of the solution is also much smaller than the AdS scale. Otherwise, you need to consider a more complicated quadratic action. Okay, but other than that, everything looks exactly the same besides this leading correction to the mass. That now involve both the string scale and the AdS scale.
So, can you know what is the capital N scale represented?
L corresponds to the characteristic size of the profile that we're going to consider for phi and chi.
Okay.
What is A?
A?
And L.
No.
Oh, yeah.
I just to make it clear.
Okay.
Okay, so, and by AdS string size, I just mean the spherically symmetric solution to the Euler-Lagrange equation of that effective action. And that's how it looks like. And the possible Lorentzian interpretation of that kind of bound set, it's a gravitational bound set because of phi, of hot strings, because chi represents the Hagedorn behavior of string theory. And the solution looks something like that. You have some profile for chi and some negative profile for phi. The fact that the profile for phi is negative corresponds to the fact that the thermal direction slightly closes. So maybe you could say it goes into the direction of the black hole solution because slightly more pinching. In any case, what's the behavior of the system? So we said that the effective action is reliable whenever beta minus beta h over beta h is much smaller than 1. But within that range, we can consider the relatively lower temperature of the regime when beta minus beta h over beta h is also much bigger than LS over LADS. Why would you do that? So the solution goes as a function of the temperature. But when the temperature is low enough, the solution is small enough such that you can ignore the curvature effect on of the solution. So when you're in this regime of the solution is small enough, so you can just copy it from the flat space answer, simply because it's small. That's the relatively low temperature regime. And for that region, you can just copy the results from previous papers on the flat space result, where you find, for example, specifically that the size of the solution L is a negative power of beta minus beta h, which explains what I was just saying, that as you increase the temperature, the solution grows. And you can also compare it to the regime of the small AdS black hole, for the high temperature regime of the small AdS black hole, where it's also small enough for you to ignore the curvature effect, AdS curvature effect on the solution, and the thermodynamics looks exactly like the one you get from flat space. And therefore, close to the transition point, also in AdS space, both sides of the transition looks exactly like how they would look like in flat space, because they're small enough. And for the same reason in flat space that you get close to the transition, that you get extrapolated result that match between each other, they'll get the same result also in anti-de Sitter space. So around the transition point, which is beta minus beta h over beta h of order 1, the size of the solution for both ends is around the string scale. And for example, the Euclidean action is Ls to the power d minus 1 over g Newton. You can compare the rest of the thermodynamic properties, and to the extent they match in flat space, and they do, they also will match in anti-de Sitter space, simply because they're small enough close to the transition point. Therefore, we have a possible black hole string transition AdS basically based in flat space. What happened in the higher temperature regime when beta minus beta h over beta h is larger than this value or around that value? So in flat space, what happened at high temperatures? The solution grows indefinitely, just like a massless particle in flat space has infinite sized length scale. In AdS, on the other hand, you have bounding potential, and specifically in AdS space, because of the mass term as rho squared over LADS squared, and the effective size of the solution stops at the Hagedorn temperature, not at infinity, but at some finite size, which is square root of Ls times LADS. So the maximal size the solution goes in AdS, it goes, and then at the Hagedorn temperature, it stays at this value, square root of Ls times LADS, which is both much larger than the string scale and much smaller than the AdS scale, which is indeed inside the regime of validity or of analysis. You can also study the behavior of the Euclidean action close to the AdS Hagedorn temperature, and unlike in flat space where it has some fractional power that depends on the dimension, in AdS space you can show it goes like beta minus beta c squared, which is what you would expect by standard lambda argument, also from the boundary point of view if you want, but just assuming that the mass is proportional to beta minus beta c. That corresponds to what you would expect in those systems. Okay. Another thing that you could do with the same effective action is to study the leading correction to the AdS Hagedorn temperature. The idea is that the AdS Hagedorn temperature is defined as the temperature at which the effective action has a normalizable zero mode. So we just tune the mass until you find a zero mode, and what we find is the following expression. So this is an expansion in Ls over LADS. To leading order, the AdS Hagedorn temperature is just the flat space Hagedorn temperature, and then you have a series of correction. This is the first correction you can find using the effective action that I was writing, and it's proportional to Ls over LADS. And recently there was a Cauchy derivation of the same formula, where I derived it from the target space. And for AdS 5 times S5, you could plug in the numbers, and you can get a prediction for the n equals 4 Hagedorn temperature, written in terms of negative powers of the tooth coupling of n equals 4. And the leading term corresponds to the flat space result, and the next leading term, 1 over 2 pi, corresponds to this correction from the curvature. I should say that one found it before me, but he didn't publish it. So. And in fact, it's profound that I noticed that this term actually matches with the integrability calculation done by Harmach and Wilhelm when they found the Hagedorn temperature of n equals 4 for every value of the truth parameter lambda numerically, and by doing a numerical fit, they actually found it 1 over 2 pi numerically. And there are several papers recently trying to looking for the next two leading order, and to the extent it's possible, they also match these terms with n equals 4 and ABGM. Again, using integrability. And third thing, before moving to AdS3, is that you can, because you're in AdS, you can imagine that just like the small AdS black hole, that the AdS string star corresponds to some sort of CFT density matrix rho, which we call our string star. And to the density matrix, you can imagine computing the CFT and time and entropy. S of A being a bulk region, capital A. And you can just follow a Falkenberg-Kubitsch and Maldacena to calculate the Renyi entropy in this background. So you construct a Renyi entropy background and look for a normalizable solution of winding strings around it. But you don't really do it, you just imagine what would happen close to n close to 1. And effectively, what you need to do in this geometry is that the temperature, so in the bulk, you have a separation of the bulk between a lowercase a and uppercase a, in A bar. And in A bar, the effective temperature is beta, and in A, the effective temperature is n times beta. And by just assuming that the linear order correction will come only by slightly changing the mass of the winding mode over here, what you get is the following answer. You get the entropy for the string star S of A is equal to the area law, area of X, X being the boundary of this region lowercase a, plus what you call the intrinsic string star entropy, which is some integral of the thermal entropy density of the string star at the region lowercase a. So we have some integral over the region lowercase a over there. So two things about that. First, unlike in the standard analysis, this can be interpreted as the matter entropy of the bulk of the safety and thermal entropy, which is usually order 1 in terms of G Newton. Here, because the matter part actually comes as part of the saddle point, this term is 1 over G Newton by itself. And because of that, it causes order 1 repulsion of the external surface. Order 1, I mean, is G Newton, but it is subleading in LS over AdS. So that's not really an effect that you have here.
I see. So you would choose a curve. So the region A is determined by some kind of curve that you have to minimize this combination.
Yeah, that's what I was trying to draw with.
Yeah, okay. Just making sure.
Yeah. Officially, at that order, I think you need to consider also higher derivative correction of the area law, but you might because you have higher orders of alpha prime. See the minimum, but yeah.
The string star is located in the center.
Yeah, it's very much located at or equal to 0 with effective size of square root of LS times LADS. So it's a very subtle effect. You need to be at almost half of the region A, just like around it maybe.
Oh, so it's okay.
To
So
actually
half
see
of
the
the star is in the A.
Sorry?
Half of the star is in the little A.
When the region capital A is half of it, then yeah, I mean, half of the star is itself, yes.
Less than half because
Well, literally at 0, I guess, it's probably exactly that. Okay, good. Yeah. In any case, this is a non-trivial contribution to the G Newton to the power -1 part of the time entropy, and you can also try to compare it with the black hole because we talk about the string black hole transition. In the black hole region, you have only the area law, but here in the AdS formulation of it, you have both the area law and the string star contribution.
I'm slightly confused by this computation we just discussed. So here, I guess the idea is that the string star is entangled with something else, right?
It's thermal state. It's just a statistical uncertainty about which of those stringy states you have.
Okay, yeah, that's right. So it's entangled with the thermal field doubles.
Yeah, with the other AdS,
Right,
something like that.
So yes, in that case, if you took half, then you would the surface will move out. It's similar to what you had on the right hand side, right?
Exactly. Half.
Yeah.
But then
Well, if the region A is half of the AdS space, right?
Yeah.
That surface will move down.
Right. Yes. So that's a non-trivial example where S of A and S of A bar are different.
Yeah,
at non-trivial order of G Newton.
Yes.
Yeah. Exactly. Yeah, and
one do the computation, let's say, for if we have one highly excited microstate of this spring and see how it change.
So I would expect something more similar if you have some thermal state in the middle, but not in terms of G Newton.
I mean, presumably, you had to input this question of whether it was in a thermal state or in a highly excited state. Should be in the some information about what when you take many copies of the saddle, you probably have to put this information in.
Information about whether
it's a single highly excited string or it's a thermal gas.
I mean the single state of highly excited.
Yes.
Yeah. I thought you meant the thermal state of highly excited string. That's what
I mean the difference between those two cases.
Yeah. So then you don't have
the surface would be different in the two cases.
Yeah. Yes. Indeed. And okay, I'm not saying here a lot, but you can also think on the same footing about the black hole thermal entropy and about the string star thermal entropy. And in both cases, in this formulation, you have an area law, just that in this case, you have another term. It's misleading to say it like that, but if you had an alpha prime exact RT formula, then you can follow it. And to the extent the black hole and the strings are related by line, then you can imagine following how these two contributions turn one into the other. I don't know how to do any of those steps. In principle, that would be interesting to understand.
Or maybe you said something about this. I missed it. In flat space, there's this nice difference, interesting difference between 4 dimensions and higher dimensions for this transition. There's no. Is there what's going on here?
So what do you mean?
I mean, in 4 dimensions, you have this sort of string ball that's growing and then it shrinks because of gravity. There's something different that happens in 4 dimensions than higher dimensions in the Horowitz-Polchinski story.
Actually,
Is there some analog of that? Are these all big black holes in AdS? Are they
these are small black holes.
They're all small dots.
So to the extent you have something funny happening close enough to the transition, it will happen here as well.
Isn't there a difference between 4 and higher dimensions? I thought that there's a difference in how this happens.
6 was the critical dimension.
Sorry?
I thought 6 was the critical dimension.
Oh, it was 4 because of the usual laws.
Maybe we're talking about
Okay,
what happened
talk about
with
this.
okay. Okay, so that's it for the general case. Now let's talk specifically about AdS3. Okay, so why would you care about AdS3? Going back to 3-dimensional flat space, there are no smooth Schwarzschild solutions, but also at least no reliable string star configurations. So we don't need to talk about the string transition, perhaps. In any case, in AdS3, we do have BTZ dipole. So you can wonder what's the relation between them and the AdS3 string star. And maybe more interesting is the fact that in AdS3, you can turn on NSNS fluxes in AdS3, and they will affect the winding string Euclidean order. So it would be interesting to understand the physics there. Okay, so what's the phase diagram in this case? So again, we have the thermal AdS solution, again with alpha beta equal to these conventions. But now we have, instead of Schwarzschild, we have the Euclidean BTZ solution with the following behavior for its Euclidean action as function of the temperature. And the first thing to notice is that unlike the previous case, if you try to find small BTZ solutions, they would go to low temperature as opposed to high temperature. So it's going to be very hard to argue why they would be connected to the Hagedorn temperature string star. So we need to do something else. Another clue is that in string theory, we have without string theory, we have asymptotically 2 circles, the time direction and the angular direction. And therefore in string theory, we have 2 U1 winding. Each of those U1 winding, one of those U1 winding is broken by the geometry. The thermal one is broken for the BTZ and the angular one for thermal AdS. So that means that if you want to connect these 2 lines, you need at least 2 phase transition instead of 1. So we need to do something slightly more complicated. And the third clue is that just like thermal AdS is tachyonic above the Hagedorn temperature, by just switching the 2 circles and considering the BTZ, it is tachyonic in the more standard sense for temperatures below what you can call the inverse Hagedorn temperature. So we have 2 interesting points now. But one is the Hagedorn temperature, the other one is the inverse Hagedorn temperature. So the easiest guess would be just like you have the string star, the AdS3 string star coming from this point, by switching 2 circles, you have another solution starts at like the inverse Hagedorn temperature and goes to the left. Both of those solutions break 2 U1 windings, and therefore it might be that they are connected by some line, and that would be our guess. So the guess would be that maybe there exists a line of Schwarzschild CFTs connecting AdS3 at Hagedorn to BTZ at inverse Hagedorn, and the description of this line close to each of those ends would be normalizable condensate of strings, here around the thermal direction, and in the other end around the angular direction. This is not my idea, other people suggested that in the past. But what we can do now is actually look at the profile of this solution at the 2 ends of the line. So this, the background that we consider is AdS3 times 3 times M4, where M4 can be additive for K3. We have thermal AdS just like we had previously, but now we have a B field proportional to lambda, and an RR gauge field proportional to square root of 1 minus lambda squared. The new thing is we have an SNS B field proportional to lambda. Lambda in our limit is a continuous number between 0 and 1, and specifically lambda equals to 1 is the interesting for our purposes and a pure NSNS solution. Okay, so we have a new parameter lambda. And now we would like to continue the discussion we had earlier using the static Witten effective field theory. So what would be the 2D effective field theory in our case? The new ingredient is the NSNS flux. And it is important because in terms of the effective 2D theory, we have the U11 form, which is just the B field after you plug in the time direction T. So if B is 2 form, A is 1 form proportional to lambda. And because the F1 string couples leading order electrically to the B field, in terms of the 2D effective action, the chi of X field is going to couple electrically to the background magnetic field that we have coming from A. So the difference is, so we have the same sort of effective action. We have the chi field, we have phi, and we have the cubic coupling phi chi squared. The difference is that now inside the derivative over here, instead of a standard derivative, we have a covariant derivative coupling this field chi to the background magnetic field A. This is this term. And what it does to leading order is to change the effective mass of this particle. So we have two contributions to the effective mass. One is m squared coming from the mass term, and the other one is g squared a squared from the covariant derivative. The first term contributes to cos squared, just like it did previously, but now we have a negative contribution from the magnetic field, which is minus lambda squared sin squared. Expanding that to leading order, we again have the flat space answer to at or equal to 0, plus a leading correction proportional to rho squared over LADS squared, just now multiplying by this new factor 1 minus lambda squared. So again, the leading order effect is the same, just with a different factor, 1 minus lambda squared. We can follow the same assumptions earlier and do the same analysis. We again find that the size of the solution is square root of LS times LADS, just now times a new factor proportional to 1 minus lambda squared. We can also find the correction to the Hagedorn temperature. But the important thing is that, unlike what we did earlier, now one of the assumptions are going to break. So the idea is that previously we had to assume that L is not smaller than the AdS scale, but now we can tune lambda to be close enough to 1 so that this assumption breaks. We're close enough to the NSNS point when 1 minus lambda squared is proportional to alpha prime over LADS squared. The LS factors cancel out, and you get that L is no longer not smaller than the AdS scale. In other words, close enough to the pure NSNS point, you need to do something more complicated. So it turns out that what you need to do is to consider a more general deformation of the NSNS field in order to account consistently for all the terms in the effective action. And what you need to do is, besides just considering a GTT deformation, you also need to consider a G phi phi deformation of the B field, and also the formation of the Middleton. And I'm not going to write the action that you get, but in terms of the coupling to the chi field, you have more complicated cubic interaction. So here we see chi squared times phi. That's the standard cubic coupling that we had so far. And now we also have coupling to this field coming from the angular direction, and another one coming from zeta, which is the B field deformation. The important thing to notice here is the sign. We have two positive contributions from the metric fluctuation and one negative contribution from the electric field, from the magnetic field that you have. So the intuition is that to the order we have a new cubic coupling, and the intuition is that the winding mode attracts gravitationally but repel electrically due to these interactions. And this is a leading order effect close enough to the NSNS point. The result is that in this regime, when 1 minus lambda squared is close enough to 0, the size of the solution is no longer square root of LS times LADS, but actually the AdS size itself. Okay, that's the new effect. And also you have a non-trivial profile, not just for chi and phi, but also for the rest of the NSNS fields in AdS3. You can also find the correction to the Hagedorn temperature. Just this time is not going to be proportional to LS over LADS, but the square of that, alpha prime over LADS squared. This is what you find in the pure NSNS case, where the Hagedorn temperature is just a function of k, an analytic function of k being alpha prime over LADS squared. Sorry, LADS squared over alpha prime. You can ask what happens specifically in the pure NSNS case, what happened at lambda equals 1. And what you find is, first of all, that the quotient descent exactly cancel, and there is no rho dependence in the mass. So the effective mass of the system is a constant, just like it was in flat space. And secondly, it's close to the Hagedorn temperature, both the swing star and the corresponding Witten tachyon become, instead of normalizable, delta function normalizable. In other words, they have non-trivial amplitude arbitrarily close to the boundary. The interpretation is that in Lorentzian space, at the NSNS point, we have the continuous spectrum of long strings. In other words, at high enough energies of the system, we have fluctuations arbitrarily close to the boundary. Because attic Witten tachyon is supposed to account for the high energy excitation of that string theory, it will have non-trivial amplitude arbitrarily close to the boundary as well. So if you want, this is an Euclidean version of the long string analysis. In both cases, the gravitational and the electric forces cancel each other. This is the Euclidean version that's supposed to account for all of these excitations in Lorentzian space. And let me just mention about the pure NSNS case that like a month ago or something like that, Aglia and Jefferies published a paper where they do this string star analysis just through the worldsheet for the pure NSNS point, where you can, in principle, think of doing it exactly in alpha pi, because for the pure NSNS point, you have an exact description of the worldsheet in alpha pi. Okay. The last thing I have to say is about confining issue, confining black holes. Sorry. So as an example, consider the D4 Witten model. This model is described as follows. So we start with 4+1 maximum supersymmetric theory compactified on S1R with antiperiodic boundary condition for the fermions. These boundary conditions are here in order to, they serve the purpose of giving a mass to the metal fields in the theory, and the tooth coupling lambda 5 is G5 squared times n and has units of distance. So together we have one dimensionless parameter, which is lambda 5 over r. As I was saying, for recoupling, which is lambda 5 over r much smaller than 1, below the KK scale, you have the weakly coupled at the UV of it. So you have weakly coupled 3+1 pure angles. So this is some sort of UV completion of 3+1 pure Young angles. On the other hand, it's strong coupling when lambda 5 over r is much larger than 1, and when n is large enough, is known to have a type 2a holographic dual with the following 10-dimensional metric. So these x's are the 4 non-compact direction, and x4 is the compact direction quantified with x4 with 2 pi r. And the idea is that f of u works such that for large enough value of u, this metric closes at the point. So we have an asymptotic S1 that closes at the point. U is the radial direction. Okay, so this is a solution that has asymptotically R31 times S1, and the S1 closes at the point. Now we can try to study the thermodynamics of that system. So instead of R31 times S1, we have R3 times S1 beta times S1R. So we have two asymptotic circles. And you can study at strong coupling what are the dominating saddles. One saddle is the thermal saddle. This is just a late continuation of the saddle I was just describing. The one into S1R closes. But you can invert the two circles, beta and R, and have another solution where the S1 beta closes. And this is the solution we call the black brain. That's the solution that dominates the ensemble at high temperatures. And that's the behavior of the free energy density. We have the thermal solution that dominates at low temperature, and the black brain solution that dominates at high temperature. Maybe you remember, but this picture is very similar to the AdS3 picture we described earlier. Just taking the AdS3 picture, you can study the system close to the Hagedorn temperature of the thermal solution and study study solutions of winding springs there. Okay, so maybe let me do it slightly slower. So you can consider a new coordinate R is proportional to u minus the value of u at which the solution, the thermal solution closes, and GTT, the time direction, looks like some factor times 1 plus r squared over l squared, where l is some curvature scale that you generate in the solution. So because this is the leading behavior of the solution, as function of r and t, we have exactly the same behavior as we had earlier in terms of the mass of the winding string. The string at the origin will have some value, and then it will go quadratically with r squared over l squared. So to leading order close enough to the Hagedorn temperature, we have exactly the same behavior as before. Because we have exactly the same equation, you can again look for the leading curvature correction to the Hagedorn temperature, and in terms of the CFT parameters, sorry, the QFT parameter, this is going to be the expansion. So the Hagedorn temperature over R is going to have the leading order this factor of lambda 5 over R, and then you have an expansion negative power of lambda 5. And as I was saying, close enough to the Hagedorn point, there is a new solution of strings winding around the common direction, but otherwise homogeneous on the non-compact direction. So we can no longer call it a string star because it's not a compact object anymore. So instead we're calling it the winding string gas saddle. But in any case, this is a normalizable condensate in terms of the u direction. Winding string homogeneous on R3 and localized at where the thermal direction closes. Yeah, sorry, when the x4 direction closes. This is u equal to u lambda, and we have the same structure, and specifically we have the same size, effective size of this profile, which is square root of LS times L, where L is again some curvature scale that we have in this background. And now here's the punchline. So at strong coupling, you can suggest a similar picture to the one we suggested for the BTZ string transition if you want. So this is the thermal solution. This is the black brane solution. And closing after the Hagedorn point, we found a new saddle that goes like that. By inverting the two cycles, we go to the black brane solution. It has its own inverse Hagedorn temperature. And because this solution exists, also that solution exists. And just like before, these two solutions break the two U1 windings, and you can suggest that maybe there's a line that connects them. Let's say there is one. This is the blue line I was drawing over here. Now we can go to weak coupling of that system. Lambda 5 over R much smaller than 1. So at very low temperatures over here, the system is described at weak coupling by 3+1 pure ion mills. We know a lot about the low temperature, about the phase diagram of pure ion mills. We know it has a confined phase. This is the gray line over here. It has Hagedorn temperature at large M, and it has a deconfined phase that becomes metastable for a little bit and then stable. That's what we know from lattice simulation, for example. But because this UV completion is invariant to switching R and beta, we also know about the high temperature behavior of that system. We have 4+1 deconfined phase, that's the black line. It has its own temperature that is dual to this Hagedorn temperature, we call the inverse Hagedorn temperature. There's this point here from which exists this line that used to be the 3+1 deconfined phase. And these two ends of the line again break two U1 windings. And you may also suggest also for this regime of lambda 5 over R that these two lines are actually connected, assuming like the minimal amount of phase transition possible or something like that by our assumption. So the idea is that what used to be the Hagedorn temperature over here on the left goes to the right over there. And what used to be the inverse Hagedorn temperature on the right here goes to the left over there, the two switch places. And if you ask what the string star, or what I call the winding string gas state over here, transform by going to weak coupling, it transforms into this region. So we describe nothing but the 3+1 deconfined phase of pure ion mirrors. Specifically, it becomes stable around this region. Canonically stable. So we don't know how to follow that line reliably, but to the extent you use this UV completion for your intuition of the behavior over here, then you get the holographic dual of the 3+1 deconfined phase is not a stringy black brane that you might expect, but it's just this string star phase over here. Of course, the whole point of the lecture is that the black hole and the string star are very hard to recognize which is which. The function of these parameters, but at least in this UV completion, this is the right picture that you should have. The dual of this phase of the 3+1 pure mills is this winding string gas solid point. That's what I was saying here. Okay, I think that's it. So let me just summarize. So first, I was describing the properties of AdS3 cells for spatial dimension bigger than 2. These coincide with flat-spaced lower temperatures because both ends of the transition become spring side. That's allowing for possible black hole string transition also in antiparticle space. But for high temperatures close to the Hagedorn temperature, the solution size goes to the square root of LS times AdS. And we can use the same effective action to find the link correction to the AdS Hagedorn temperature and to match it with integrability. For AdS3, I suggested different BTZ string transition. And for almost NSNS backgrounds, we saw that the solution size goes to the AdS size due to the electric repulsion from the NSNS flux. And lastly, I was describing a new binding string saddle for confining backgrounds. You can also compute the linear correction to the Hagedorn temperature and suggest a new sort of black brane string transition for the system. And if you believe everything I said, you can also show that this new phase is actually related to the 3+1 deconfined phase of pure ion mills. That's it.
Say again why this new phase is related to the deconfined phase. I thought that was the phase with no black hole.
Just if you follow the line.
The last point in 3.
Yeah.
Maybe I missed this. Yeah.
So this line is this line. After you go from strong coupling to recoupling, that's the low temperature dominant phase in both ends. That's the Hagedorn temperature of that phase. It goes to this line. And if there's a line that comes out of it that breaks 2U unwinding, it goes not to this line. Just the line that is slightly not stable and not stable in 3+1. So the black brain solution here corresponds to the very high temperature regime of that system.
You're saying there are 2 transitions?
Which picture? Sorry.
At weak coupling, I'm not sure what the statement is in 3+1.
Okay, so
Weak coupling.
yeah, so the claim that you have one like Hawking page like transition here, I guess another one over here.
Are we supposed to have just the first order transition similar to what we have for the black hole phase between confined and deconfined phase? Maybe I'm mistaken.
It's not the thing where there's supposed to be a huge free energy difference between the 2 phases.
Exactly, but at scale 1 of R, we start getting, at the scale 1 of R, it's not the same as the 3+1 of, so we get scale anymore. There we start getting this confined modes and it starts.
This is the 3+1 theory. Wait, the 3+1 confinement deconfinement is this one.
I understand it's not the same as the black hole, but it's not the same. It's not described by this geometry, right? But aren't we supposed to have a first order transition between confined and deconfined phases?
Yeah,
that's a specific
transition.
Where is
there?
that?
It's first order.
I would have expected the black line and the gray line to cross at the first order transition. Why is there a gap between 2 temperatures? So, okay, maybe I'll ask differently. Where is the first order transition? At what temperature is it on this horizontal axis?
The first one is here. Are you asking where this one?
No, the plot on the right.
Yes.
I think you're saying there is a first order transition between the confined and some deconfined phases. Maybe there are 2 first order transitions. So
yeah.
Yes. Okay, so the one on the right is between confined and deconfined. What is the one on the left?
I'm not sure, but it's in 4+1. It's above the KK scale.
For one of the other parameter would be the polycle loop around the usual Euclidean tangent.
Okay, so here, okay, sorry, now I understand. I thought, okay, I was, okay, now I understand what you're talking about. Fine, I was just.
I have a general question. In 3 dimensions, I think there's there are even in flat space there are black hole-like solutions for horizons. Myers, who was it? Emparan and Horowitz found in the mid-2000s. You have masses that are really big, close to G Newton, that almost close up the space. They give you a depth angle that almost close up the space entirely. And then, so then the Casimir energy is important, and you actually get solutions with the horizon. Do you know if anyone has looked at what the analog of string stars would be for the same thing, where you put in? So again, you'd have to make it exciting enough to have mass very close to M Planck, and to see if the counting works also in that case. It's a very different kind of entropy. There's no H bar of the entropy. The H bar cancels out. It's the whole
Yeah,
horizon.
but how could you take them to the strings? But you couldn't take them to the string scale to be coupled.
Sorry?
Since they're at the Planck scale, but no, if you connect them to the string scale, it's struck to couplings.
Well, but you could just try to see if it's heading in that, I mean, in a similar way. It's kind of same thing is true here, right? I mean, right at the moment, right at the transition, everything's.
Yeah, right.
I don't see it. It's not qualitatively. Just one. It's just another regime where you do have something like a holo, but it's more mechanical. The entropy doesn't have an H bar.
Yeah, I don't know about that.
Okay, I was just curious if anyone has looked at it. Yeah. It's a very nice paper. It was Emperor Myers and Horowitz. Any other questions for? All right, if not, I remind you, we'll be going to a gathering in the lobby for dinner around 6 o'clock. Anyone interested, let me know. And let's thank Weizmann for a terrific talk.